Imagine an AI agent navigating a maze, not just once, but again and again with the goal constantly shifting, obstacles changing, and new tools suddenly appearing. In the real world, environments don't stay still. Goals evolve. Rules shift. Capabilities expand. Yet most reinforcement learning agents are built under the assumption that everything is fixed, that the world is a static Markov decision process. When reality breaks that assumption, these agents fail. But what if we could build agents that adapt on the fly, not by retraining from scratch, but by learning to recognize change, respond intelligently, and keep building on what they already know? Today, we dive into MORPHIN, a self-adaptive Q-learning framework designed to solve one of the toughest challenges in real-world reinforcement learning, non-stationary environments. Let's break this down. In traditional reinforcement learning, agents learn policies through trial and error, updating their value estimates using the Bellman equation. The core update rule for Q-learning is simple. QSA left arrow QSA plus alpha times. But this works only when the environment is stable, when rewards don't shift, and the set of available actions stays the same. In reality, that's rarely true. Imagine a traffic signal controller. At rush hour, congestion spikes. The optimal policy changes. You need to prioritize one lane over another. Then after the peak, traffic drops. Now you want to minimize idle time. The reward function has changed. The goal isn't just to reduce wait times, it's to balance efficiency and fairness. Or consider a robot in a warehouse. It learns to move boxes efficiently. Then a new feature is added, a jump action to leap over obstacles. The agent must now integrate this new capability into its existing policy, without forgetting how to navigate the old way. These are concept drifts, changes in the underlying dynamics of the environment. And they're common. Yet standard Q-learning struggles. Why? Because once the agent converges, it locks in its policy. It stops exploring. When the goal shifts or the action space expands, it's stuck, like a driver who only knows one route, even when the destination moves. MORPHIN solves this by combining two powerful ideas: real-time concept drift detection and adaptive learning dynamics. Here's how it works. At the heart of MORPHIN is a Page-Hinkley test, a statistical method that monitors the stream of cumulative episode rewards. Think of it as a heartbeat monitor for the agent's performance. If the average reward starts deviating significantly from its running mean, that's a red flag. A concept drift is likely occurring. When the drift is detected, MORPHIN triggers an immediate response. The exploration rate epsilon is reset to 1, forcing the agent to re-explore the environment. The learning rate alpha is dynamically adjusted based on the temporal difference, TD, error, which measures how wrong the agent's predictions are. The key innovation. The learning rate alpha isn't fixed. It scales with the magnitude of the TD error. Alpha equals alpha plus alpha max minus alpha, 1 plus E minus TD error minus K. So when the environment changes, and the agent suddenly sees large discrepancies between predicted and actual rewards, the TD error spikes. That drives alpha upward, accelerating learning. As the agent stabilizes, the TD error drops and alpha decays back to baseline, ensuring convergence. This dual mechanism, forced re-exploration paired with adaptive learning speed, allows MORPHIN to relearn quickly while preserving prior knowledge. And here's the crucial part: the Q table is never reset. Unlike methods that reinitialize or maintain multiple models, MORPHIN keeps a single Q table. Existing Q values serve as an informed starting point. This prevents catastrophic forgetting, the phenomenon where new learning erases old knowledge. Now, what about expanding action spaces? Say a new jump action appears. MORPHIN detects this as a drift, because the agent suddenly has more options and the reward structure changes. The framework dynamically expands the Q table by adding a new row for the new action, initialized to 0. Then it resets exploration and adapts the learning rate, just like with a goal shift. This unified response means MORPHIN handles both reward function changes and action space expansions with the same mechanism. We tested MORPHIN in 2 scenarios. First, a 9x9 grid world with 2 challenges. Goal relocation. The target switches every 300 episodes between opposite corners. Action space expansion. At episode 300, a jump action is introduced, allowing the agent to bypass obstacles. Compared to a standard Q-learning agent with a fixed exploration schedule, MORPHIN adapts dramatically faster. While the baseline agent gets stuck, committed to an obsolete policy, MORPHIN detects the drift, re-explores, and converges again, all without forgetting previous goals. In the traffic signal control simulation, we modeled a 2-lane intersection. The reward penalizes both congestion and inefficient green time allocation. We induce drifts by changing vehicle arrival rates. After episode 3000, when traffic increased, MORPHIN detected the drift via the Page-Hinkley test. It responded by increasing exploration and accelerating learning, and performance recovered rapidly. The baseline agent, however, suffered prolonged degradation. One limitation emerged. When traffic later decreased, the new reward distribution was a subset of previous values. The pH test didn't trigger because the mean didn't shift enough. This highlights a key challenge. Drift detectors must be sensitive enough to catch meaningful changes, but not so sensitive that they trigger falsely. Still, the results are compelling. In the grid world benchmark, MORPHIN improved learning efficiency by up to 1.7 times, measured in total steps to convergence. It adapted after every drift. The baseline failed to recover after the first shift. So what makes MORPHIN special? It's not just a new algorithm. It's a synthesis, a unified, lightweight framework that brings together established techniques into a single reactive system. It uses the Page-Hinkley test for detection. It leverages TD errors for dynamic learning rate adjustment. It preserves knowledge through a single Q-table. And it enables continual learning without retraining. This aligns with the principles of continual reinforcement learning, where agents should never stop learning. And it fits perfectly into self-adaptive systems, like smart traffic control, IoT networks, or robotic systems that must evolve in real time. Looking ahead, the future of MORPHIN lies in scaling. Can we extend it to deep reinforcement learning? To high-dimensional state spaces? To multi-agent systems? And can we replace the pH test with more robust drift detectors, ones that can catch subset-based drifts? There's also the question of hyperparameter tuning. Right now, parameters like the sensitivity threshold H and the TD error threshold K are set empirically. We need systematic analysis to understand their impact across environments. But the core idea is clear. Adaptation should be built into the learning process, not bolted on. In a world where environments are never truly stationary, MORPHIN shows us a path forward, one where agents don't just learn, but learn to change. They don't just survive change. They thrive in it. And that's not just a step towards smarter AI. It's a leap toward truly autonomous, self-adaptive systems that can operate in the real world.